So, let us get started. Let us think about the n queens problem. Now, this n queens problem, is it a satisfaction problem or an optimization problem? Satisfaction problem. We are not optimizing quote unquote anything, we are just interested in making sure all the constraints are satisfied, which means that all the no two queens are attacking, right. But we have to formulate it as an optimization problem now, and a state would be a solution. So, let us say this is our solution. Now, we have to come up with an objective function which is analogous to the original objective function of the satisfaction problem when optimized fully. So, what can be an appropriate objective function here? Number of kills that can be made, or alternatively number of pairs of queens that attack each other. So, if I am in an 8 cross 8 board, what is the maximum number of pairs of queens that can attack each other? 8C2, which is 28, and what is the minimum number of pairs of queens which can attack each other? 0. That is when I would have found the solution, and I want to minimize this or maximize this? Minimize this. So, what have we done? We have converted our satisfaction problem into now an optimization problem, not unlike minimize the number of constraints dissatisfied, right, not unlike that. So, basically we defined a new function, some people can call it a heuristic function, but though this is not the heuristic function as we had been studying earlier. So, I prefer to use the word objective function. Think of it as the objective function. The objective function is number of pairs of queens that are attacking each other, and for this state if you do all the counting you will come to 17. For example, you know, this queen in the first column is attacking the queen in the fifth column, the queen in the first column is attacking the queens in the second and third column, and so you will keep adding 1 for each such pairs of queens which are attacking each other. So, you will get h equal to 17 or heuristic or optimization function equal to 17 for this state. Now, I have defined an objective function. Let us also talk about a state. What will be a possible state? Now, notice in local search a state is a solution, good or bad, and now we have defined the notion of good or bad. Good is which has all constraints satisfied or lower constraints dissatisfied, and bad is which has higher constraints not satisfied. So, we have defined the notion of good and bad, but what are all our states? What are all our states? Somebody raise your hand, somebody from that end of the class. What is the state for local search in the n queens problem? Anybody? Yes, Vaibhav. All possible solutions. All possible solutions. So, in a solution how many queens should be on the board? 8, all 8 of them. And now we can be smarter. We can say let us add at least some constraint to my state space. So, we will say we will have at most 1 queen per column. We do not have to, but let us say we say that. So, let us say we say that no more than 1 queen in a column, exactly 1 queen in every column. So, now how many states do I have? How many states do I have? 8 to the power 8, because the first column can have at most 8 positions for the queen, the second column can have at most 8 positions for the queen, and so on and so forth, not at most, exactly 8 positions for the queen, and in the end all the 8 columns can have up to exactly 8 positions for the queen. So, you multiply all of them and you get 8 to the power 8. So, for an n cross n board you have n to the power n solutions that you want to search in. So, it is a huge search space, right. So far so good. Now, what have we done? We have defined the notion of a state. Acha, this is important that this is so different from how we defined in the previous set of slides in systematic search. There we said a state is a partial configuration. Initially no queen is on the board, in the first depth exactly 1 queen is on the board, in the second depth exactly 2 queens are on the board. So, we were searching in partial solutions. Here we are searching in the solution space, and this is the fundamental difference between systematic search and local search. Fundamental difference with respect to how we model problems typically. Okay. Nobody is saying that you can't model it that way here and what not, but what works? What works is that in local search we search in the solution space. Why? Because if we had partial states here and at some point we just return one of the solutions, we may end up outputting a partial solution, then obviously that will not be considered valid. Okay. So, now we have defined state, we have defined the objective function. There is one other really important thing that we need to define in order to define the local search completely, and this notion is the notion of a successor function or the notion of a neighborhood. Okay. Now, this is very important because there is a little bit of divergence with respect to how the notion of successor was defined earlier when we were doing goal based search, goal directed search. The difference was that my solution was a sequence of actions, and the semantics of the action, whatever was the action supposed to do, that was in my successor function. So, if I am in this world state and if I apply this action, which is the state I will go to, that is the state that the successor function gave me. Here my solutions are all independent of each other. I mean, I have one possible state shown here, which is a specific configuration of these queens. I may have another possible state where the first column queen is in the first row, the second column queen is in the third row, and so on and so forth. What do you mean by moving from one state to another state? That is not a notion that the problem is giving me. That is a notion that I need to artificially define, and this is what we are going to call the neighborhood function. And the intuition of the neighborhood function is that two states in the neighborhood of each other are relatively similar solutions. So, let us think about this. Let us think about it from the context of the example, because that is going to make it clearer. Let us say I give you this state, this full configuration of n queens, 8 queens, and I say that you need to come up with some neighborhood function that takes you from this state to a similar solution, this solution to a similar solution. Can you come up with one such proposal for neighborhood function? Yes, what is your name? Chinmay. Yes, Chinmay. The neighborhood state could be one state where position of 7 queens is the same and only 1 queen is moved. Now, can you say that these two solutions are similar to each other? Let us first understand what that means. So, Chinmay says only 1 queen should differ. So, first I need to pick which queen differs. Let us say the first queen differs. How many places can I move this to? 7. So, I will say that I have 7 neighbors where the first queen is moved. Similarly, I will have 7 neighbors whether the second queen is moved. So, how many neighbors will I have for the state? 56, 8 times 7. Now, this neighborhood function Chinmay brought out from his pocket. Okay. Somebody else could have brought out another neighborhood function. What neighborhood function would you think about? Something different. It's not very hard. You can come up with another neighborhood function. Yes. What's your name? Jay. Move one queen with just one step. So, then if I do this, what is the maximum number of neighbors? 16. or in the worst case it may be only 8 if you all the queens are in one row at the end, right. So, this will have only 6 neighbors at best. Somebody could come up with a more wacky neighborhood function. What might you say? Move as many number of queens wherever you want. You can do that, right? And how many neighbors would I have then? 8 to the power 8 minus 1. Why? Because all states are now my neighbors. Makes sense? This is not that difficult, right? So, now we have 3 candidates. Let us think about this. First candidate is move only one queen one step. Second candidate is move one queen anywhere in the column. Third candidate is move as many number of queens anywhere in their respective columns. What are the strengths and weaknesses of these neighborhood functions? Okay, which one is obviously terrible? The last one. Why is it obviously terrible? Because I can't even look at all my neighbors. It's so large. And if I can look at it basically means brute force search, and we don't want to do that. Obviously a bad idea. On the other hand, if I am too restrictive in my neighborhood space, then what's going to happen is that the solution that I am looking for may require a lot of steps, and moreover you may have to, and we will come back to that very soon, but you may have to go through, you may have to go down before you start going up more often than not. Never mind. So, the point is that a good neighborhood function should be one which has a good balance between the immediate number of states I have to look at my immediate neighborhood and the path to the length of the path to the solution in general. Okay. And therefore, what is a good neighborhood function is a learned acquired skill. It is very hard to a priori say that this is a good neighborhood function or that is a good neighborhood function. You have to try some neighborhood functions and then say, okay, this neighborhood function makes sense to me in the context of this problem, or you can try it in actual implementation and see. So, okay, so where we are, we have converted our n queens problem into the local search formulation. We have defined a state, all queens on the board, one in each column. We have defined a neighborhood function, move a single queen to another square in the same column, and we have defined a optimization function, the number of pairs of queens that are attacking each other.